This is an intro to complex numbers here. What is a complex number, first of all? It's an expression of the form a plus bi, where a and b are real numbers, and I is called the imaginary unit. It has the property that its square is -1. Why do complex numbers exist? Does the imaginary unit exist? Yes, because we say so. That's why they exist. There's no philosophical issue at all, not in the least. People used to think there was a philosophical issue. Now, that's why they're called that's called an imaginary number. Is you're making that up. It's not a real number. That is the origin of those words. But they're just as real numbers. They're mathematical objects that we can define addition, subtraction, multiplication, and division on. And it's a consistent kind of arithmetic. All the properties of algebra you would want to be true are true. It's got geometric interpretations that are very beautiful. And on Monday, we're going to see that it leads to complex functions that take a complex number as input and give you a complex number as output. And it's visualizing those functions that is the coolest part of an introduction to complex numbers. And we'll relate to the Riemann hypothesis as well. How do you add them? You add them as if they were polynomials in I, as if I were a variable. You add the parts that don't involve an I, and you add the parts that do involve an I as if they're like terms. In other words, you get A plus C plus B plus D with the I factored out. By the way, the terms that do not involve an I are called the real part of the complex number, and the term that does involve the I, that's next to the I, is called the imaginary part. This is the real part. The plain old B, which is a real number, that's next to the I, is called the imaginary part. So you add complex numbers by adding their real parts, also adding their imaginary parts and keeping the I where it is. This does have a nice geometric interpretation, which is worth briefly describing here. If you make a plane and axes, coordinate axes in this plane, we usually label these X and Y. But in complex analysis, you label them differently. You label this one real and this one imaginary. But it's there. I drew it. It's there. Okay, it's just as real as the real axis. It's just a label. Okay, a fun label. That's all it is. A complex number, instead of being a point on a number line, it's a point in the complex plane. A two-dimensional point. If this point represents A plus BI, that means its rectangular coordinates are A and B. So this represents the number A on the real axis. This number represents the number actually BI on the imaginary axis, B times I. But yeah, the second coordinate is B. The I is just a label for imaginary axis. And when you add complex numbers, it's actually better to think of them as being vectors. Just like when we did motion, you could associate these points with position vectors, starting at the origin. An arrow going from the origin to the point. I could do it for that complex number. I could do it for, say, a complex number right here. Maybe its real part is C, its imaginary part is D. And you add them by the parallelogram law. You make this parallelogram. And the sum, as an arrow, starts at the origin and goes to the opposite tip of the parallelogram. That point right there corresponds to the complex number A plus C plus B plus DI. You add them as if you're adding them as vectors. You can also subtract them. A plus bi minus c plus di. You subtract their real parts in the same order, and you subtract their imaginary parts in the same order. As a concrete example, we could both do 2 plus 7i plus 3 minus 4i and 2 plus 7i minus 3 minus 4i. In the first case, when you add them, 2 plus 3 is 5. 7 plus negative 4 is 3, and keep the I there. In the second case, subtract the corresponding real and imaginary parts. 2 minus 3 is negative 1. 7i minus negative 4i is positive 11i. Complex number subtraction can be interpreted in terms of vectors as well. In terms of vector subtraction, if you know about that. I'm not assuming all of you know about that. What about complex multiplication? A plus bi times c plus di. You multiply them as if they're linear polynomials in I, but with a catch. What's the catch? Well, let's do it first. FOIL, use the FOIL method. First times first is A times C. Outside times outside is A times D times I. Inside times inside is B times C times I. And last times last is B times D times I, I squared. This is not incorrect. However, it's not as simple as it could be. Anywhere you see an I squared, replace it with a negative 1. Once you've replaced I squared with negative 1, then this term becomes negative BD and doesn't involve an I anymore. And the real part of the answer is AC minus BD. And the imaginary part comes from these two terms as AD plus BC. Keep the I outside the parentheses. If I multiplied 2 plus 7i and 3 minus 4i, I'll do it by foiling. 2 times 3 is 6. Outside times outside is minus 8i. Inside times inside is plus 21i. And last times last is minus 28i squared. I squared is negative 1, so this whole thing becomes plus 28. 28 plus 6 is 34. Negative 8i plus 21i is plus 13i. To check this on Mathematica, you'd want to use a capital I for the imaginary unit. So, for example, we could do 2 plus 7 times capital I times 3 minus 4 times capital I, 34 plus 13i. Mathematica is using a funny looking I instead of a capital I. You can get the funny looking I to show up on your screen as well by doing escape, double I escape, I believe. Yep, there it is. Also representing the imaginary unit. Don't believe me, do this. Squared, get negative 1. Finally, what about dividing? Let's just do it for a particular example. I'll do 2 plus 7i divided by 3 minus 4i. 2 plus 7i divided by 3 minus 4i. How do you deal with this? It's a trick. What you do is you'd like to get rid of the i's in the bottom of this fraction. And ultimately write this as some number plus some number times I. The trick is to multiply the top and the bottom by the complex conjugate of the bottom, where you keep the real part the same, but negate the imaginary part, change the minus to a plus. If I multiply it in the bottom, I got to compensate by multiplying on the top, so that I'm really multiplying by 1 and not changing the value of the expression. But now you've got a FOIL, both in the top and the bottom. Watch what happens in the bottom when you FOIL. 3 times 3 is 9. Outside times outside is plus 12i. Inside times inside is minus 12i. Those will cancel. And then last times last is minus 16i squared. I squared is -1, so this is the same as plus 16. On the top, the i's don't go away. 2 times 3 is 6. 2 times 4i is plus 8i. 7i times 3 is plus 21i. And then I get plus 28i squared. The i's do not completely go away. That does become -28. 6 minus 28 is -22. 8i plus 21i is plus 29i. The i's canceled on the bottom. We're left with 9 plus 16 is 25. And then you split this into two fractions. -22 over 25 plus 29 over 25 times I. And let's see if it's right. 2 plus 7i divided by 3 minus 4i. Yes, the right answer. Okay. Complex multiplication and division have geometric interpretations as well. Even more beautiful interpretations, in fact, than complex number addition and subtraction. And in fact, the geometric interpretation of complex multiplication and division is the key thing that makes complex analysis useful, actually. It's beautiful and also the reason why it's useful when you get down to the core reason.